How do we undo multiplication? Division. So if I had some type of equation like 2x equals 6, okay, because you see the multiplication here, to undo that multiplication, you use division, you get x to be 3, right? Okay. How do I undo addition? Subtraction. So subtract 3, right? How do I undo powers of 2? Square root. Okay, so give me x equals 4, right? How do I undo square roots? I square. Okay, so if I want to undo something operational wise, like adding, I subtract. Or if I want to undo subtraction, I add, right? If I want to undo multiplication, I do division. Or if I want to undo division, I do multiplication, right? We've extended that into working with square roots and powers of 2. We can do the same thing with powers of 3 and cube roots and so forth. But those are referred to as what type of operations? What kind of word do we use? They're inverse operations. Good. Okay? Whenever somebody says that they are inverses, it means one undoes the other. Okay? Think about this. If I look at, come on. My mouse stopped. There you go. Let's say we look at a graph like x squared. And I'm only going to look at part of it. So let's say if x is bigger than 0, then let's look at x squared. So I'm looking at that graph right there. Okay. And then over here, what is the inverse of x squared? What undoes x squared? Square root. You just told me. Square root. Okay. So I'm going to look over here at the square root of x on that graph. Okay. Would you guys agree that those structures of the graphs kind of look similar? Okay. And the reason they look similar, let's look at this one over here. Let's put some points on there. Let's go 0, 0. That's over there. Let's go, 1, 1 is over there. 2, 4. And let's go 3, 9. Okay. So if I look at those 4 points, and let's look at their ordered pairs, they are those. Okay. Now, help me out. If I choose over here so this is a square root of x, so let's let x be 0. What's the square root of 0? What number multiplied by itself 2 times gives me 0? 0. So 0, 0 will be on that graph. Okay. Let's take the x value of 1. If x is 1, what's the square root of 1? 1. Okay. What's the next value over here that would be easy to take the square root of? 4, right? What's the square root of 4? 2. So 4, 2. And the next one would be 9, 3. So let's look at those points. How do the points on these inverses relate to one another? If I look at point A and compare it to E, they're the same thing, right? If I look at B and compare it to F, they're kind of the same thing. Right. When I look at C and I compare it to G, okay, they're not flipping quadrants, but the coordinates switch spots, right? If C is 2, 4, then G is 4, 2. We change the X and the Y, right? Okay. That happens because they are inverses. And what that means then is if I put in, let's say that we have let's say we have the relationship that we'll just call this function over here f. So f is equal to x squared, and this one is g and that is equal to the square root of x. Okay? So you start over here with x being 3. If I put x to be 3 here, I got to put 3 here, right? And that leads me to 9. I'm now going to take 9 and put it there, which means I have to put it in here, right? And with this bit back. 3. I started with a value, and as I run it through those two functions, did it get me back to what I started with? Did those two functions start with a random value? Did those two functions do something to that value and then ultimately undo it? Yeah, we made that value turn into 9, and then we undid that turning into 9. Inverses do that. Okay, inverses undo each other. What's nice about that is that is a tool that allows us to solve equations. Okay, so where am I going with this? Our goal eventually, I'm going to give you some exponential equations. I'm going to give you an equation when there's a variable in the exponent. I'm going to ask you, what does that x value have to be? And the way you're going to do that, because we've done it already with square roots, say. So if I give you square root of x plus 3 equals 10, you subtract 3, you get square root of x equals 7, and then you'll use the inverse. Once you get down to that last step, you use the inverse of the radical x to get what x is, right? Square both sides with x be 49. That's using the inverse as a tool to solve for a variable. We'll do the same thing with exponentials, but we've got to figure out what is the exponential's inverse. Okay? So an exponential's inverse. Okay? These two things, all inverse functions are reflections across the line y equals x. Okay? So if I take, let's just clean some stuff up here real quick. If I look at the line y equals x, okay, that line right there. If I put a point like 2, 4 over here, okay, and do exactly what we just taught. If 2, 4 is the point on the original function, then what is the point on its inverse? 4, 2. So I'm going to see 4, 2 by using this reflection tool in GeoGebra. I'm going to click on that point, click on that, and it's going to reflect it. Where did it reflect it to? It reflected it to 4, 2. This was 2, 4, reflected to 4, 2. Okay? So GeoGebra has this tool of reflection for us. So let me show you this then. Okay? If I take x squared the positive portion of x squared, okay? And I'm looking at the positive portion because I can't take the square root of a negative, so we don't want this part over here. And I ask, so when I click on reflect about a line, when I click this, it's just like it's clicking that 2, 4, but it's clicking the 3, 9, it's clicking the 4, 16, it's clicking all of the ordered pairs on that thing, and it's going to reflect them all at once. Well, if I reflect them all at once, it gives me that orange curve there. Okay, let me change the color of it. So that blue one. So the orange one was x squared. It generates this blue curve. Now, it shows it in GeoGebra as a parametric curve, and we don't have enough math yet to understand what that is. But if I type in square root of x, does it land as that purple one land directly on top of the blue one? So what we're seeing here is that purple one must be the inverse of that orange one. Orange one was x squared, purple one was square root of x. They must undo each other. Okay? So an exponential has the same thing. Okay? I'm going to show you an exponential function. Okay? So remember, exponentials, we can change the base to whatever we want it to be. So I'm going to just say 2, and I'm going to raise it to the x. We got that function right there, correct? If I have the line y equals x, and I reflect this thing over the line y equals x, that new curve, that red curve, is the inverse of the exponential. Okay? This inverse of an exponential is called a logarithm. Okay? And we're going to try to investigate what a logarithm is and how we deal with it. Okay? Exponentials are what we call one-to-one functions, which means they pass, because they function, they pass the vertical line test. You guys remember that? Talking about the vertical line test. Basically means that every x value has one, there's an R in there, has one and only one y value. Okay, so every x value has one and only one y value. And the reason we talk about it and define it as a function, give it a new name instead of just calling it an equation, is because when I say here's an equation, you don't know that every x value has one or only one y value. It could have two. But when I tell you here is an equation that is a function, you know this condition is met for that new equation. Okay, it's much like I say here is a student. You don't know what that student is. You don't know if they're a sophomore, freshman, junior, senior, right? But when I tell you here is a senior, you now know more information about that particular student, right? Okay, so same idea. Okay, a function is still an equation, but you know more about it. It's a special type. Okay, so functions are objects that they pass the vertical line test. Okay, in order to be a function that has an inverse, it has to also pass the horizontal line test. Okay, which the horizontal line test says every y value has one and only one x value. Okay? So what I'm telling you here is, to be a function, I say everybody look at the y value that goes with x. If it's a function, everybody will be looking at the exact same y value. Does that make sense? Okay? To pass the horizontal line test, I would say everybody give me the x value that goes with this one y value. And everybody would give me back the same exact x value. Okay? So let me show you an image of this. This is, so the easiest function that we've talked about so far this year to talk about functions is x squared. So I just want to look at that function. Let's go x squared. Would everybody agree that if I said everybody give me the y value that goes back with x being 2, that you'd all give me the y value of 4 back? Okay. Nobody's going to get something different, correct? So we can do that for every x value. And when we can do that for every x value, and everybody give me the exact same y value back, then you're all going to give me, we're all going to be on the same page, so then that means that this thing has to pass the the vertical line test. So this thing would be a function. Is that okay with everybody? Okay. Now, if I asked every one of you, give me the x value. Give me the x value that pairs with the y value of 4. Okay? What x value pairs with a y value of 4? 2 and negative 2. So here, some of you are going to tell me 2, some of you are going to tell me negative 2. So what we would say is that this thing does not pass the horizontal line test. So this thing cannot have an inverse. Okay? But we know that it does. Square root is the inverse, but we can't take the square root of a negative number. That's why I've been looking at this instead when I said if x is greater than 0, show me x squared. Now I eliminate your option of negative 2, right? Now if I say everybody give me the x value that goes with 4, you're all going to tell me 2, right? Or if I ask you, give me the y value that goes with 2, you're all going to give me 4. So this is a function that passes the vertical line test and the horizontal line test. And with that, if you have a function that does that, it's going to have an inverse. Okay? And if it's going to have an inverse, we say it's 1-to-1. Okay? 1-to-1 because basically it meets the condition of being a function that has an inverse. It passes the vertical line test and the horizontal line test. 1-to-1 really means every x value has one y value. Every y value has one x value. Okay? Does that make sense? Okay? The reason I cannot just look at x squared, So when I take an inverse of, when I take this inverse, okay, which is the reflection across the line y equals x, it's going to give me this. And what I'm hoping for is that this purple one is a function, okay? So a function's inverse still has to be a function. Does that make sense? Okay. So this has to be a function. This has to pass the vertical line test. Well, if I took x squared like that and asked for its inverse, which would be the reflection across the line y equals x, it would be that curve right there, correct? Change color. Let's do it this way. So this orange curve is the reflection of x squared across the line y equals x. Does this pass the vertical line test? To pass the vertical line test, you can only intersect it one time, right? This intersects two times, doesn't it? So this would not be a function. And it's not a function because if I told you all or asked you all, everybody tell me the y value that goes with x being 4, what are some of you going to tell me? -2 or 2. Okay, so we're not all on the same page, right? The idea of functions and passing vertical line test and passing horizontal line test and all that kind of stuff is so that you can be on the same page as me. When I say what's the x value that goes with 4, you can tell me. When I say what's the y value that goes with 4, you can tell me. We'll all have the same answer. Does that make sense? The one thing I need you to understand, though, is that the only types of functions that have inverses are the ones that pass the horizontal line test. Well, our exponential does that. Okay? So here it says this means they have an inverse. Our exponential functions are going to have an inverse. We have a inverse. So it's nice. The things that we've talked about so far, like the square root and the square function, x squared and square root, they're inverses and their names relate to each other really well. Cube root and power of 3, or cubed function and root 3, or cube 3. They work really well in regards to how we name them. Exponential and logarithm, those names are completely different. Okay, but a logarithm is the inverse of an exponential. Okay. When we work with logarithms, okay, it's going to be the first type of equation that you guys have seen that does this. It's going to put a word in our equation. The word log, L-O-G, will be in our equation, okay? And the notation starts to look confusing, all right? But hopefully through my examples here, we kind of show you what we really mean by a logarithm. And it's a lot like, basically it's a symbol for another number, okay? You guys remember square roots being a symbol for another number? Okay, logarithm, the notation that we give is really the same thing. Okay, it says by definition, a logarithm is a quantity representing the power, or our exponent, to which a fixed number, which is going to be our base, must be raised to produce a given number. Okay. Logarithm is a quantity representing the power or exponent to which a fixed number, the base, must be raised to produce a given number. A lot of people ask me, what's the question? What is a logarithm? The short of it, the short answer to that is it's an exponent. Okay? But it's an exponent that I use to get a number that I'm already defined, or that I'm interested in. Okay? So there you see a logarithm is an exponent that a base is raised to generate another value, and that value is usually given or something that I already am interested in knowing. Okay, so the following is the mathematical definition of a logarithm. Okay, right now we know this. Right now that's an exponential, right? Okay, the way to find its inverse is to take those components and rewrite them over here as those components. Okay? So over here, that was called the b, right? Or the base. B was the base. Over here in the logarithm, it's a subscript. Okay? It's a small number written at the bottom of the word log, but that is the base. That value right there is the exact same thing in the exponential. Okay? You see here y. Okay? So here we're taking a base and raising it to a number to get x. Base raised to an exponent to get x. That's what we talked about for an exponential, right? Here, okay, we have an equation right here that says this right there, this logarithm will tell you what that y value is. That was the exponent over here. Does that make sense? Okay. So the logarithm is a value, a quantity in which I raise the base to get x. Okay. That's the general. We're going to use that format here on a regular basis to work through these examples. But hopefully these examples explain to us what is going on. Right now, when I say, basically we're going to ask us to solve for x. Okay? X right now, with that notation, x is an exponent. Okay? X is an exponent. And it's the exponent that I take 8 and raise 8 to. So basically I'm asking myself, how many times should I multiply 8 by itself to get 32? Okay? Well, if you think about that, 8 times 8 gives me 64 right away, right? So there I'd be multiplying it by itself twice to get 64, a number that's greater than 32. So does it make sense that when we do this, that the number that I'm going to get back should be less than 2? Does that make sense? If I multiply 8 by itself once, I get 8. If I multiply 8 by itself twice, I get 64. Well, 32 is between 8 and 64, so this logarithm must be between 1 and 2. Okay? So this is how we're going to do this. Okay? Basically, I'm going to write down 8. So if I look at this right here, okay, I'm going to rewrite it in that format right there. So I'm going to take the b value. So what's the b value over here in this? It's going to be the 8. Okay? Then I'm going to take the y value, okay, which is that number all by itself on the other side of the equal sign. Now, in some problems, it might actually be represented with a different letter, okay, but it's the object that is all by itself on the right-hand side of this equation. So this object right there is going to be the x. Does that make sense? Okay. Equals, okay, so the x that I'm using here, when I change it to exponential, becomes the thing that's isolated on the right-hand side of the exponential. So that x right here is the 32 right there. Does that make sense? So we're just looking at, I don't care what the letters are, what the numbers are, I'm taking these parts and rewrite them in that positioning. Does that right there, does that elicit the idea that 8 raised to what number, I'm saying what number because it's a variable in this case, so I don't know it, will equal 32? Does that make sense? So now what I'm going to do is because our calculators will do this, so you have to use Desmos with this, okay? Because your TI-83s, 84s right now will not work with 8 as the base, okay? Your calculator only works right now with 10 and the number E, which we haven't talked about too much. So we're going to go to Desmos, okay? And we actually might even have to go to the graphing Desmos. I don't even see, you guys see the logarithm on here? Well, okay, it's got log, but doesn't let me use, okay, so we have to go to the graphing one. It's a little bit, it's got a calculator on here that's a little bit more involved. If I go over to the miscellaneous tab, you see this one right here, it says log with that little subscript right there. Click on that, and now it lets me fill in what I want right there. So it's 8, and then we had 32 in there. Okay, and we get 1.66666, which is 4/3 or sorry, 5/3. It's 5/3 as the value that I take 8 and raise it. So tell me what that exponent is. So let's do this. Let's say, so that is the x value that when I take 8 and raise it to the 5/3 power, does it spit back 32? Okay. So this number here, okay, that expression right there is a symbol for that number right there. Does that make sense? And it's the exponent then that I take that number that is my base in my exponential format and raise it to get the 32. Okay? I think it's confusing. Okay? But hopefully enough examples will help you see this. But it's a lot like radical 16. When I say radical 16, that symbol is nothing. It has something to do with 16, but it's not 16, right? It's not even close to 16 on the number line. Okay? Radical 16 is a symbol for the number 4, right? Okay? This is a symbol for a number that is not, it's related to 8 and 32, but it's not even close to either of them. This is a symbol for 5/3. And 5/3 is the number that I take 8 and raise it to, so it's the exponent that I raise my base to get this 32. Okay? And the purpose of this, the reason we're talking about this in general, and any class will talk about this, is because eventually my question will be, if I have 2 to the x plus 3, and that is equal to 5, what value of x are we looking for here? And the only way you can solve that is to understand logarithms. Okay? So that's where we're going with this. It'll be several days before we get to those equations. I want to focus more on this stuff right here. Okay? So let's do another example. How can I take this? Okay, what would my base be in this one right here? 4. Okay? So I'm going to take the 4. You'll see me draw this picture a lot. I'll go 4, I'll draw an arrow all the way across the equal sign, and that tells me my exponent. And then I'll draw another arrow coming back to that, and that tells me the right-hand side. Okay, so I always draw that little picture. And I phrase it to myself, 4 to the x will give me 256. 4 to the x will give me 256. So I don't know what 4 to the x is. I don't know what x is. So, 4 to the first gives me 4. 4 squared gives me 16. 4 to the third gives me 64. 4 to the fourth, what's 64 times 4? Is that 256? Okay. So we should see here that we should get a 4 back. Okay. Let's see if we do. Let's go to our calculator. And I'll put a base of 4. And here we'll put 256. And we see that we do get 4 back, right? So what that means to me is that 4, my base, raised to this exponent, which is equivalent to this number right here. So 4 will give me 256. That make sense? Okay. Another way I can view that, and like I said, that this here is the same thing as that 4. I could actually take my base of 4 and raise it to, let's raise it to this thing. Let's go cut Control C and we'll Control V. So 4 raised to that number, which is a symbol for 4, is 256. You guys do the next one on your own. Log base 3 of 81. Rewrite it in exponential form, and then take your calculator and actually tell me what x is. Or maybe some of these you might not need a calculator. Some of them you might know from your understanding of exponentials what x is. Yep. Yep. All right, so again, I'm going to start with a 3 as my base. Raise it to the what? You're going to take your base, and you're going to come across, you're going to raise it to the x, and that will come back and give me 81, right? Okay, so this is what I was saying a minute ago, is that sometimes you might know, based on your understanding of exponents, what x has to be. If I go 3 times 3, that would be 9, right? 3 times 3 times 3 would be 27. 27 times 3 is 81, right? So that would be 27 times 3. That's actually 3 times 3 times 3 times 3, right? It's 4 3's being multiplied together. So it tells me x had to be 4. Okay? And if we go back to Desmos, log base 3. Oh. Log base 3 of 81 does indeed give me that 4. So we could see that 3 raised to the 4th power does give me 81. Okay. The nice thing about this is that the logarithm will work for things that aren't whole exponents. Okay. So like 3 times 3 times 3 times 3 gives me 81. But what if I don't want to multiply 3 by itself a complete 4 times? Maybe I want to multiply by itself a complete, I don't want to say complete, but like 3.5 times, okay, or 3.25 times. Logarithms allow for that. Okay. What's this? So this one here is, you know, if I want to multiply 5 by itself, how many times to get 27? So 5 to the x, come back and give me 27. Well, think about this. What's 5 to the first? 5. What's 5 squared? 25. 25 is pretty close to 27, right? Okay. So our x value should be pretty close to 2. Does that make sense? Because 5 squared is 25. So something a little bit bigger than 2 should be what I get when I take 5 and raise it to a power to get 27. So let's see what Desmos gives us. So I'm going to go 5 to the 27, or log base 5 of 27. So we said if we went with this being 25, we would have gotten 2 on the dot, right? Okay. But 27 is that. So now basically, and this is where I think it gets kind of confusing, and I don't know how to explain this other than using exponents, okay? Because we know if I say 5 squared, that means 5 times 5, right? If I say 5 to the third, that means 5 times 5 times 5. If I say 5 to the fourth, it's 5 times 5 times 5 times 5, right? It's telling you how many times to multiply 5 by itself. But if I say 5 times, or 5 raised to 2.047, well, I know that's 5 times 5, but a little bit more. Does that make sense? Okay, because that 2.047 is more than just multiplying by itself twice. It's multiplying by itself 2.047 times. Okay, so, but if I take 5 and raise it to that number, okay, Control C, Control V, okay, it gives me back 27. The reason it doesn't give me back 27 on the dot is because that 6 all the way at the end right here is rounded, okay? So when you cut and paste using a rounded value, and it's going to probably, a lot of times they'll give you like 26.999999999, or in this case, it went above 27, 27.0000001. Let's see here. We can go the other direction, okay? We can go the other direction. In this case, you have to decide, okay, that obviously we see a true equation here, right? 49 equals 7 squared, okay? But a lot of times they ask you to rewrite an exponential expression into a logarithmic expression, okay? Or an exponential equation into a logarithmic equation. So this is the what. And find our exponential. What would we call that? What word do we call that 7? Yep, that's our base. So 7 is our base. 2 is our exponent. Okay? And 49, okay, we'll talk about what we'll call 49 here in a little bit, but let's see if we can go ahead and rewrite this, because we're starting with that format now, and we're going to go to this format. Okay? So I'm going to write the word log down. Okay? This b, which we said was our base, right, ends up being the b that goes right there. So for us, we said the base was 7, right? Okay? The exponent, okay, which over here is y, when we change it into this format, becomes that y. So our exponent right now is 2. So 2 should go there, right? Okay? And the x that was over here, the thing that is all by itself, which in our problem was 49, becomes that right there in the logarithm. So we'll put 49 right there. Okay? This thing right here, the 49, or that x in the logarithm, is called the argument. Okay? It's just the word we use for usually any function that is a word. Okay, log. You guys heard of sine, cosine, and tangent? You guys do that in geometry last year? Okay. The angle in sine, cosine, and tangent is referred to as the argument. Okay, it's just a thing in parentheses. So yes. Okay. But now let's look at this. Is this true? Would you guys agree if 7 raised to the second, does that come back and give you 49? 7 raised to the second comes back and gives you 49. Let's do this one. Okay, what's the base on that one going to be? It's going to be 10. Okay. That should, so 10 is the base. The exponent then is the thing that in the logarithmic form is the thing that's by itself. Because a logarithm, this is the idea, the logarithm is an exponent. That's what the definition said. So this is saying logarithm is the exponent. What was the exponent? It was 3. Okay. So what is the only thing left over that can go here then? 1,000. Would you guys agree that 10 raised to the third is 1,000? And initially, and we're going to spend more time on this next week, we want to go through a practice and make sure that we are very versed in being able to flip-flop between exponential formats and logarithmic formats, because it's going to be very important for us to do that when we solve equations. Okay, you guys remember the other day when I said Ella said she wanted to buy a brand new Jeep Rubicon, right? Okay, $50,000 car, and we figured out that it's going to take, if she had $3,000 to start with in her bank account, and I think we were giving her like a 5% interest rate or something like that. That it was going to she was going to have to let that money sit in 142 years, 442 years, right? The way that we find that 142 years is through the use of logarithms. Okay, so that's kind of where this is going in the next several days. We'll probably spend at least all of next week working on logarithms, if not into the following week, and then we'll get into, hopefully at the end of that, identifying how we solve some equations with logarithms. All right. Okay, tomorrow I'm going to post a assignment in the